Hello, and welcome back to the Unity Foundations tutorial. Today we will look at core principles of C# programming and how we can use them when working with the Unity engine. We'll cover application entry points, variables and modifiers, classes and instantiation, and providing dependencies. Let's get started. Let's quickly discuss the lifecycle of a C# program. If you want to follow along for this part, open up Visual Studio. If you don't have Visual Studio installed, you can refer to the previous video for how to add the Visual Studio module to your Unity installation, or you can download it from the link in the description. To create an empty C# project in Visual Studio, go to File, New Project, select the console application, check the Do Not Use Top-Level Statements box, hit Continue, and then choose your project name and a location for your project. This will create a solution file with a single class called program and a static void main function. So what is a program? Well, it's a series of instructions with an entry point, some lines of logic, and an exit point, and also, oftentimes, a return value. Our C# program expects a single master entry point, a static function called main. It then runs line by line, executing this program. We hit the run button, you'll see we get the console.writeLine method runs, and here's our output, hello world, and then the application finishes. As a next step, we can define variables, create new instances of a class, and run logic. But after all of this runs, the program completes, and all of these instances and variables cease to exist. In order to persist our application's lifecycle, we can use the console.readLine method inside of main. This pauses execution of the main thread until the application receives some user input. Then it continues and exits as normal. Here we go, we've started the program. I'll just type some input, I hit return. The input is printed out through our console.writeLine, and then we exit the program as normal. Here we have an async method called startCounter. An async method creates another thread which runs separately from our main application. When we run the program, main calls startCounter and then continues to the console.readLine, which suspends the main thread. In the meantime, startCounter continues on its own. And you can see here we've got a never-ending loop that, while true, we will await for 1,000 milliseconds or 1 second. We increase our duration counter by 1, and then we write out the new duration. And so you'll see here, I start the program, and now it begins printing out these durations, and this is running on a separate thread from the main. Main is still waiting for input, and so as soon as I type something, you'll see that it completes and exits the program, and it terminates everything. When working inside the Unity editor, there is no single entry point. The program lifecycle is handled by the Unity engine, and the program will run until we hit the stop button in the editor, or explicitly request for the program to stop in a script by calling application.quit. So if there's no entry point, how do we execute the code? Well, our entry point into working with the Unity application is through GameObjects and MonoBehaviours. A MonoBehavior is a custom script which extends Unity's base MonoBehaviour class. This allows it to be placed as a component onto a GameObject. The Unity engine has a series of predefined functions which act as entry points into that particular instance of the script on that particular GameObject. Right now, in our MonoBehaviour, I have one debug statement logging the word awake when the awake method is called. You can see when we start up the application and the active game object is in an active scene and it becomes instantiated, and the MonoBehavior becomes instantiated, we get the awake function being called and logging as we'd expect. Now, if I disable the GameObject and I run the application again, you'll see the awake function is not called until I activate the GameObject. Now, no matter how many times I activate and deactivate the GameObject, the awake method is only called the first time that the GameObject becomes active in an active scene. Additionally, even if the script is disabled, the MonoBehavior is disabled, when the GameObject becomes active, the awake method is called on that MonoBehavior. The second entry point that the Unity application offers into our MonoBehavior is the OnEnable method. You can see that when our active GameObject with an enabled script is instantiated into the scene, after the awake method, the OnEnable method is called. The OnEnabled method will be called every time that the script becomes active, as long as the GameObject itself is also active. You can see enabling and disabling the script on a disabled GameObject does nothing, whereas enabling and disabling the script on an active GameObject calls OnEnable every time. The third entry point into our script is the start method. The start method runs after the OnEnable method and only the first time that the GameObject and the script become active. If we disable the script and then re-enable it, we only get the OnEnable method. If we disable the GameObject and re-enable it, we only get the OnEnable method. Remember, each GameObject in your hierarchy is a separate instance, and so each script on that GameObject is also a separate instance. I've updated our MonoBehavior to include the name of the GameObject that it's calling. And so when we run our application, now that we have first object and second object, each with the MonoBehavior that we've written, we're going to see in our console that we are getting awake called from the second object, followed by OnEnable called from the second object, followed by awake from the first object, followed by OnEnable from the first object, and then finally start from the second object and start then called from the first object. Note that both of the GameObject's awake and OnEnable methods were called before either of the start methods, but that we had no control over which GameObject was called first. The order in which GameObjects are called is handled behind the scenes by Unity and is generally not guaranteed. An important concept to understand is that when working in edit mode, the GameObjects and components that we see actually exist as instances very similarly to their runtime counterparts. They can be referenced and are capable of storing instance variable values and executing logic, even in edit mode. To demonstrate this, I've made some changes to our MyFirstMonoBehavior class. I've added an integer field, order and hierarchy, with a default value of -1. I've also added an updateOrder method, which sets that value to the GameObject's order in the hierarchy, and a printOrder method, which logs the value. I've also added the context menu attributes to both of these methods, which exposes them in the editor through the context menu on the MonoBehavior. Lastly, I've asked it to print the order when the awake method is called on GameObject instantiation. Note that the order in the hierarchy is retrieved by referencing the GameObject to which this component is attached, and then the transform component on that GameObject. Both the GameObject and the transform component exist in the Unity editor, even when we're not in play mode. When we call the print order method through the context menu, you can see we get the default value of -1. When we call the update order and then the print order methods again, you can see that that value has been updated and is stored on this instance of the MonoBehavior. However, when we enter play mode, the value is reset as if the GameObject had just been initialized. Here it is, printed from the awake function, and it's reverted back to -1. We can update the order, print the order, and we'll see that it has now in play mode updated and holds a value of 3. But when we exit play mode and return to edit mode, if we ask it to print the order again, you'll see that even in edit mode, it has now reverted back to its initial default value of -1. There are two reasons why this happens. Firstly, when we enter play mode, Unity creates a temporary runtime environment and populates it with clones of our edit mode objects. This is why changes you make to game objects and components in play mode do not persist when you return to edit mode. This includes changing hierarchy positions and any changes you make to components. When we exit play mode, you can see this reverts to the way it was before we entered. Secondly is serialization. Serialization is the ability for data to be recorded and reconstructed. By default, Unity does not serialize private variables. So the value cannot be passed to the play mode clone and cannot be reconstructed by the original object when we return to edit mode. We can explicitly mark a private field with the SerializeField attribute in order to allow it to be saved. By serializing the field, we also gain the ability to see and set that value on the instance through the inspector. Now that the value is serialized, changes that I make in edit mode will persist into play mode. Changes that I make in play mode will not persist, but the original value is still reconstructed when returning to edit mode. In addition to the SerializeField attribute, there are two other attributes which can be used to control visibility in the inspector and serialization. I've updated our MonoBehavior again to have 6 string fields and 2 methods. We have 3 private strings. The second 2 are marked for serialization, and the third is marked to be hidden. We also have 3 public strings. By default, Unity will attempt to serialize your public fields, so they will persist their values and they will be shown in the editor. We can ask Unity not to serialize a field with the non-serialized attribute, and we can hide a value in the inspector using the hide in inspector attribute. Combining these attributes gives us control over visibility, editability, and persistence of our instance variables. The uppercase method updates the values stored on our strings, and the print values method prints those values. When I add the component to our game object, you can see all the fields are initialized with their default lowercase values. When I run the uppercase method and then print the values, you can see that all fields have been assigned uppercase values. When we enter play mode and run the print values again, we can see that the private non-serialized string has reverted, the private serialized string is visible and has maintained its value, the private serialized hidden string still not visible but maintained its value. The public string maintained its value and is visible. The non-serialized public string did not maintain its value, and the public hidden variable maintained its value but is not visible in the inspector. Now that we've covered the effects of modifiers and attributes within Unity, let's consider how they affect providing dependencies. Generally, the more contained your code is, the easier it is to debug. so I recommend using private fields and methods whenever possible. For dependencies, the most contained option is for an instance to provide its own dependencies. If that dependency is an instance of some non-behavior class, like this list, we can give it a default value, serialize the field, or assign a value in the awake method. Any of these options will ensure that the dependency is filled. However, mixing them together can cause unexpected results. When a component with a serialized field is added to a GameObject, the value is populated with the provided default. However, once created, that value is now stored on the instance. If the default value is changed, the new value will populate new instances of the component, but existing instances will hold their stored value. And because the awake method runs at playtime after the component is cloned, assigning a value in the awake method will of course overwrite any serialized value and any initialization value. There is no one-size-fits-all solution. Just remember that mixing serialization, default values, and initialization in the awake method can make things a bit harder to follow. If I need to see a field's value for debugging purposes, but I don't need to tweak it in the editor, I will sometimes serialize the value for visibility, but initialize the value in the awake method, because it ensures I don't accidentally change the initial value. But what if that dependency is another GameObject or a component in our scene? It already exists, so we don't need to instantiate it. But how do we get a reference? The most straightforward way is to leverage SerializeFields and assign the references through the inspector, which ensures that it will be available at runtime. Note that for components, you can drag the GameObject with the component onto that field, and the component will populate in, assuming that the GameObject has the component on it. The downside is that if you change the name of your variable values due to a refactor or a typo, when you return to the scene, these references will be lost, and you will need to reassign them via the inspector. An alternate method for grabbing a component dependency is to use the GetComponent method, preferably in your awake function, so that the request is only made once and the dependency is satisfied as soon as possible. You can combine this with the requireComponent attribute, which automatically enforces the presence of the component specified on the GameObject, and therefore that the dependency will always be satisfied. You can see that adding the MyFirstMonoBehavior component to the GameObject also added the animator component because of the requireComponent attribute. A possible downside to requiring the component is that it forces a particular GameObject and component structure. Using GetComponent in children allows for flexibility in your GameObject structure, but it also prevents enforcing the presence of the dependency. The method that works best will depend on the specifics of your situation. Congratulations on completing the MonoBehavior Foundations tutorial. We covered a lot of ground and some complex topics. If you have any questions, drop it in the comments. In the next video, we'll cover the scriptable object class and scene assets. For more practice working with MonoBehaviors, try the 4th mission of the Unity Essentials pathway called Programming Essentials. You can access the pathway from the link in the description or by creating a new project with the Unity Essentials Learning Template.